I have recently been delving into research on black holes, which has seen significant progress since I last discussed it. The big question posed by Stephen Hawking in the late 1970s and early 1980s, what happens to matter that falls into a black hole, has gained new insights. The current progress, although largely theoretical, is thrilling as researchers explore the mysteries of these cosmic giants. While theoretical work is the primary method, we now also have photographs of black holes captured using radio telescopes. One of these is Sagittarius A at the center of our galaxy, a small, supermassive black hole with a mass of 6 million times that of our Sun. Another well-known image comes from the M87 galaxy, 55 million light-years away, showing a black hole with 6 billion times the mass of the Sun. If you're interested in fascinating content like this, be sure to subscribe to Space Exploring and give this video a like. The scale of these black holes is mind-boggling. For instance, if our Sun were compressed to a radius of just 3 kilometers, it would become a black hole. In contrast, the M87 black hole has a Schwarzschild radius larger than our entire solar system. These two images, along with advances in detecting gravitational waves, are helping scientists deepen their understanding of black holes and their properties. The photograph of the M87 black hole showcases an accretion disk, a flat, rotating disk of matter emitting radiation. The light in this image is bent by the gravitational pull of the black hole, a phenomenon predicted by Einstein's theory of relativity in 1915. When the first photo was captured a few years ago, it closely matched Einstein's prediction, marking a significant achievement in astrophysics. Alongside these images, scientists have also detected gravitational waves from colliding black holes, which create ripples in space-time during their violent mergers. These gravitational waves travel across the universe, affecting even our surroundings on a minuscule level. The concept, famously described by physicist Kip Thorne as a storm in time, refers to how these cosmic events can ripple through the very fabric of space and time. Currently, advanced detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, can pick up these disturbances, even though the events that cause them occur millions of light-years away. LIGO operates with laser beams set at right angles, one facility in Washington state and another in Louisiana. This configuration allows scientists to measure tiny shifts caused by gravitational waves. Even though these shifts are extremely small, the detection capability of LIGO has opened up a new way to observe and study cosmic events, revealing new information about black hole collisions and the dynamic nature of our universe. The distortion in space-time caused by gravitational waves is measured with extreme precision, even smaller than the diameter of an atomic nucleus. LIGO, an advanced scientific instrument, uses 2 laser beams to detect these ripples with high accuracy. This technology has allowed scientists to gather data on black hole collisions and other cosmic events, providing invaluable insights. While these discoveries are significant, theoretical advances have also shed new light on previous calculations, including those by Stephen Hawking, which once challenged prevailing scientific thought. Before diving deeper, remember to subscribe to Space Exploring and give this video a like to stay updated with more fascinating insights into the universe. Back in 1974, Stephen Hawking made a groundbreaking calculation that black holes, once thought to be entities from which nothing could escape, actually emit radiation, now known as Hawking radiation. This discovery was so crucial that it's immortalized on his memorial stone in Westminster Abbey, alongside luminaries like Newton and Shakespeare. According to his calculations, black holes glow at a very low temperature and, as a result, gradually shrink over time, suggesting that they have a finite lifespan. Hawking's findings raised a significant question. What happens to the information that falls into a black hole? His calculations suggested that there is no trace of this information in the emitted radiation, implying that black holes fundamentally destroy information. This was a startling concept because in all other areas of physics, information is never truly lost. Even if an object were destroyed, theoretically, its information could be recovered from the radiation and remnants. In physics, information refers to the fundamental properties of particles and their arrangement. The laws of nature suggest that information remains intact, albeit highly scrambled, even if the object is incinerated or vaporized. However, according to Hawking's calculations, black holes seem to be the only phenomenon in the universe where this information is entirely erased, with zero traces left in the emitted radiation. This idea, known as the information paradox, posed a profound challenge to our understanding of the universe. Hawking's groundbreaking work showed that the radiation emitted by black holes comes from their event horizon. The event horizon is the point of no return. Once something crosses this boundary, it can never escape. If the sun were to be compressed into a 3-kilometer radius, it would create a black hole with an event horizon at that point. Interestingly, if someone fell through the event horizon of a black hole in the Milky Way, they wouldn't even notice the transition until it was too late to escape. If we were to cross the event horizon of a supermassive black hole, we wouldn't immediately notice anything unusual. For us, it would feel like empty space, and while we might be talking outside of the event horizon, by the end of a simple sentence, we could already be inside. According to Einstein's theory, this transition happens seamlessly, with no immediate awareness. The real change occurs as we are pulled towards the singularity, an infinitely dense point. The central question then becomes, what is the singularity? In Einstein's theory, the answer is that it's the end of time itself. The extreme warping of space and time by the black hole causes everything to mix and distort, leading to this enigmatic endpoint. If you find this concept fascinating, be sure to subscribe to Space Exploring and give this video a like. Your support allows us to dive deep into the mysteries of the universe, bringing you more content on black holes, space, and the theories that challenge our understanding of reality. The singularity, as described, isn't just a dense point, but rather the end of time and space as we know it. This can be visualized as space and time flipping over and getting so entangled that a definitive endline emerges. In Einstein's 1915 theory of general relativity, this is illustrated as a literal line beyond which the future does not exist. However, while this paints a clear picture, physicists believe that there is much more to understand beyond this line, suggesting that Einstein's model, although groundbreaking, is not the full story. We are only beginning to get hints about what might happen beyond the singularity. A significant paradox arises from calculations related to black holes, specifically the black hole information paradox. This paradox stems from the event horizon, a point of no return that distorts space and even disrupts the vacuum, creating radiation. This Hawking radiation seems to come from empty space, unrelated to anything that falls into the black hole. But the central mystery remains: why is there no information in this radiation, and where does the information of fallen objects go? This leads to a major conflict in our understanding of physics. The fundamental laws of nature suggest that information can never be truly destroyed, yet calculations based on black holes imply that information is lost forever within them. This contradiction sparked intense interest in the 1980s and continues to challenge physicists today, revealing the limits of our knowledge and urging us to dig deeper into the mysterious nature of black holes.